Welcome to this video discussing the solution to exercise 1714, which it's quite an involved one. This was a difficult problem. So in this problem, we are saying that we're taking every non-zero rational number x, we write it as p over q, where p and q are integers with no common factors and q is greater than 0. So if x is negative, the negative is put on p, not q. And then we define f of x to just be 1 over q. Right, whatever this q is here for the number x. And then f of 0 is 1, f of x is 0 for all real numbers that are not rational, so for all the irrational numbers. And so then there's some examples. F of x is 1 for each integer, because if you have an integer, then p over q is just equal to p, because q is equal to 1 for all the integers, and the way they set up this problem. And then you have like f of 1/2 or negative 1/2. And again, that negative 1/2, like that negative is really on the 1. It's not on the 2. F of 3/2 of so on. Basically, f of any fraction in its simplified form of p over q is just going to be that 1 over q. So f of 1/2, f of negative 1/2, f of 3/2, they're all going to be equal to 1/2. And then you're supposed to show f is continuous at all the irrational numbers and it's discontinuous on all the rational numbers. So I'm just giving the scratch work. I'm giving rather detailed scratch work of this argument, though. So let x be an irrational number. And so right away, we know that it's equal to 0, right? Because that's what this says. F is 0 on the irrational numbers. And then imagine that you let xn be some sequence that converges to x. So I'm not writing a proof, so I should write like let xn be a sequence of the reals that converges to x, but I'm just giving you the idea of the scratch work. If this sequence xn is completely contained in the irrationals, then f of xn is equal to 0 for all n, and so the convergence is completely trivial because you just have a constant sequence of zeros. So then the real question is, well, what happens if that sequence of numbers were all rational? Then by the setup of this problem, you would write that sequence xn as a sequence of pn over qn, and the sequence of function values associated with that set of inputs, sequence of inputs, would be 1 over qn. And so then you have to say, well, if I'm going to show continuity, because that's what I'm tasked with showing, is that it is continuous at these points that are irrational, then I need to show, that's what this NTS means, I need to show that 1 over qn goes to 0. And since we said that the way we write these q's is that they're all greater than 0, that means by theorem 910, you go look it up, that the qn terms actually have to be going to positive infinity. So that's like you kind of go through that line of logic and say, all right, that's what I actually need to prove continuity, is that qn goes to positive infinity. Then you have to ask yourself the question, why should it? So suppose that the lim_inf of qn was a natural number. And I'm actually specifying it to be a natural number because these are integers, right? P and Q are always chosen to be integers based by what the problem said. So there's no way that a sequence of integers is going to be anything other than an integer. And because these Q's, the denominators, were taken to be greater than 0, I know just the positive integers are at play for possible limits of the sequence Qn or positive infinity. So I'm saying, well, imagine that the lim_inf was actually, a finite number, right? Because if the lim_inf was positive infinity, then I would have this. So what I'm going to try to show is that I get a contradiction. If the lim_inf is some natural number, I'm going to try to arrive at a contradiction to say, well, then this cannot happen. What can only happen is that the lim_inf is positive infinity, which makes the limit positive infinity. So I say, okay, here's what I'm going to do then. If that happened, if I could suppose this, then that means that because of the lim_inf being the infimum of the set of subsequential limits, I can actually extract a subsequence that has as its limit the lim_inf. So that's exactly what I do. And I'll just say, well, then I'll let Q equal this lim_inf because I don't want to write lim_inf all the time. I just want to write Q. So now what do I have? Well, theorem 11.3 is telling me that P sub nk over Q sub nk is converging to some x, right? So I say, okay, well, I have that. It's converging to some number. Well, actually, excuse me. I'm having this number because xn converges to x, and xn is written as this sequence of numbers, and that means that any subsequence has to converge to the same thing. That's what's happening here. So all the subsequences have the same limit. And my claim is that if P and K converges, P and K over Q and K converges to X, then that means that P and K has to have as its limit Q times X, because Q is the limit of this Q and K. So in other words, I'm saying P and K has to also have a limit. Seems reasonable because I'm taking a ratio that's converging, and it sure seems like if the denominator converges, the numerator should also converge. But then here's kind of the problem. Qx is not rational because remember, x was taken to be an irrational number. So since q is an integer, you take an integer and multiply it to an irrational number, you're left with an irrational number. So that means that this is a little strange because P and K is, again, just like the Q and Ks, it's some subset of the integers, right? And I'm using the signed integers. That's that kind of interesting Z symbol to indicate positive or negative integers, because that's where if it's negative, that's where the sign's going, is on the P's, on the numerators. So that means if P and K converges, it must actually be converging to an integer, since it's complete. But we'll kind of ignore what that means for now. Just that's what would have to seem to logically happen. So that would mean that this convergence would then be a contradiction if I could actually show that this is what has to happen. So let's see if we can show that this has to happen, because then ultimately what we get is the only option is that the QNs diverge to positive infinity. So let me try to prove this claim, because the proof of this claim is in the keys to the kingdom. It tells me exactly what I want, that the QNs have to diverge to positive infinity because there is no way the limit could be finite. So the way I prove this is I assume it's false. Assume to the contrary, that if Q and K converges to Q and P and K over Q and K converges to X, that P sub n K as a subsequence actually doesn't converge to QX. Then if it does converge to R, to a number R that's not equal to QX, so it's not that it diverges, it's just it's convergent, just not to this number. Well, then this contradicts the uniqueness of limits, because R over Q is not going to be equal to X, because R over Q is going to be a rational number. You say, okay, so that can't happen. So then I say, well, what if it just diverges altogether? If it diverges altogether, then that means that the lim inf is less than the lim sup, right? Because there's no limit in this case. Well, so choose subsequences, P sub n sub K sub L and P sub K sub n, such that the P sub K sub L, that subsequence of a subsequence, that one actually has as its limit the lim inf of whatever this subsequence P and K is, and P sub n sub K sub n has the limit as the lim sup. I know that's a lot to digest. You might have to pause this video at various times to actually just sit and think about what's going on here. P and K is already a subsequence. So I am saying if that subsequence does not converge, in this case, like I'm saying, it can't. If I'm assuming to the contrary, it's not converging to QX. This first statement I have is that, well, it can't converge to something else. So then I'm saying, well, then that means it has to just diverge, and the lim inf has to be less than the lim sup of the subsequence P and K. And then what I'm saying is, well, that means that there's subsequences of this subsequence that have as their limits the lim inf and lim sup of the subsequence P and K. So that's a lot, again, to digest, but hopefully you get it. You might have to listen to that a few times. In either case, because Q and K is a convergent subsequence, its corresponding subsequences, where you use the same indices, have to also converge to Q, again by the same theorem, that if a convergent sequence has its subsequences converge to the same limit. And then by the uniqueness of limits, I end up saying, well, that means that the subsequences of these subsequences, these ratios, they're all converging to X, yet by construction, I've made it so that these ratios of these two different subsequences actually have different limits. And again, this contradicts the uniqueness of limits, much like this contradicted the uniqueness of limits up here. So again, a lot to digest there, but this basically tells you that the only thing that could happen is P sub n K has to converge to QX, if that's the case. And so then that tells us that if P sub, so this gets us basically to this contradiction, right? We have that if P sub n K converges to QX and it's not rational, then we're going to get this lim inf being infinite and the QN diverges. But I did say, I want to show, maybe can we prove this, that if P sub n K converges, it has to be to an integer. That's what this last part is saying is that, hey, if P sub n converges, it eventually becomes constant. And I'm just going to leave this up on the video so you can pause it and read and see why. I want you to try to digest what I'm doing here, because the main key is that if I have a convergent sequence, it's Cauchy. And if it's a convergent sequence of integers, all the integers are a distance at least one apart from each other. So if I let epsilon be chosen to be greater than 0, I should say, maybe like greater than 0, but less than 1, then if it's a Cauchy sequence, eventually all the terms get within that distance from each other. And that means that eventually all the terms have to become the same number, because I've chosen this epsilon less than the distance between any two integers. And so then there's this easy part to the proof. And again, I'll leave this kind of up there for you to read and try to digest. But if you suppose Qx was a rational number, then all you have to do is basically choose a sequence of irrational numbers that are always then equal to 0, or the function values are always equal to 0, and yet the function value is this 1 over q, which is not 0. And so you don't have convergence of the function values, so the function is discontinuous. So very easy with sequential continuity to prove discontinuity on the rationals, but a lot is involved to prove continuity on the irrationals, as I kind of scroll back up so you can get the full scope of the length of this proof. So that's it. That's kind of a long discussion, but I hope you could follow at least parts of it. You might have to watch that a few times. Thanks for listening.